Warm greetings to my respected teachers and all my viewers. I am JyotiYadav, student of MERI College, course MCA in batch 2018 to 21. In this video, I will be going to cover the topic breadth first search. So, before learning what is breadth first search, let's see why we use breadth first search for graph traversal. The process of visiting and exploring a graph is called graph traversal. To be more specific, we can say that exploring each and every vertex and edge in a graph where we explore each vertex exactly once is known as graph traversal. There are two types of graph traversal techniques. First is breadth first search, second is depth first search. So we are going to learn breadth first search. So BFS algorithm is a graph traversing technique where you select random initial node, or you can say root node, and start traversing the graph in such a way that you traverse all the nodes and its children's. So before moving further, let's see two important terms related to graph traversal. First is visiting a node. Visiting a node means selecting a node, and exploring a node means selecting a node and exploring its children's, finding its children's. So the main data structure involved in BFS is a queue. A queue is a data structure that follows FIFO methodology. FIFO methodology means first in, first out methodology, where the data inserted first is accessed first and removed first. So the queue is open from both the ends. From one end, we add the data, and from the other, we remove the data. So this is the algorithm for BFS. So let's take a queue and start finding the goal node. So first we will see if the queue is empty or not. If the queue is empty, then we will return failure. Else we will see if the node is a goal node. If the selected node is a goal node, then we will return the path from the root node to the goal node. If the node is not a goal node, then we will expand it, and we will find the children's of that node and insert the children's into the back of the queue and remove the node. So let's see an example for it. So this is a example you are seeing on the screen, and let's take this example, and we have to find the node G. So G is our goal node. So initially we are having A as the root node, and we insert A into the queue. So we will see if A is our goal node or not. So A is not our goal node. So we will see that we will remove A from the queue, and we will expand it and find that B and C are the childrens of A. So we are going to add B and C into the queue. So we will see, we are seeing that B is the first data into the queue. So we are going to remove B from the queue, and we are expanding it. B is not our goal node. So we will remove it, and the children's D and E, the children's of B, D and E are added into the back of the queue. So now we are having C as the first node into the queue. So we will see that if C is our goal node or no. So C is not our goal node. So we will expand it, and we are seeing that D and G are the childs of C. So we are going to add D and G at the back of the queue. So now we are seeing that D is the first data into the queue. So we are going to see that if D is our goal node or not. So no, D is not our goal node. We have to find G. So we will remove D from the queue and expand it. So we can see that C and F are the childrens of D. So we are going to add C and F at the back of the queue. Now we are having E as the node into the queue. So we will see E is our goal node or not. So E is not our goal node. So we are going to remove E from the queue and expand it. We can see that E does not have any childrens. So no node will be added into the queue. Now we will see that D is the first node into the queue. So we will see if D is our goal node or not. So D is not our goal node. So we will going to add B and F childrens of D into the back of the queue. Now we are having G as the first data into the queue, and we are seeing that G is our goal node. So we select G for expansion, and it was found to be a goal node. So the algorithm will return the path from initial node to the goal node. Here you can see the algorithm. If we find the node as a goal node, then we are going to return the path from the root node, initial node, to the goal node. So here we are having A as the root node, and we are going to return the path from A to G. So we are going to return A, C, G, and terminate the algorithm. So we are getting ACG as our path. So we will learn what are the advantages of BFS. You can see that we are having G at four locations into this graph. So you can see that we are finding G which is more closer to the root node. So it is finding the shortest path into the graph. So we can see that while we were traversing according to the levels. First we have traversed A, then B, C at level 1, then D, E, D, G at level 2. So we are traversing according to the level. Here we are seeing there is nothing like useless path in BFS, since it searches level by level. Then it is finding the closest goal, the shortest path in less time. Of course, if the goal is more closer, then it will take less time because it is searching level by level. Disadvantages of BFS is it is consuming more memory. We can see that all the connected vertices must be stored into the memory. Because we are using queue, it is of course storing the nodes into the queue, and it will require more memory. So properties of BFS are: it is complete, of course, optimal if it follows shortest path first. The complexity of BFS is big O of BD, where B is the branch factor. Branch factor is calculated using the number of childrens. Each we can see that if in this we are having A, we are having two childrens of A, we are having two childrens of D, but we do not have two childrens of E. So we can say that if we do not have uniform childrens, then we can find the branching factor, average branch. We can calculate the average branching factor. And here D stands for the depth of the goal node, where the goal node is located. We can see here we are having the depth as 2, here we are having the depth as 1, 2, 3, 4. So depth is calculated by levels. So that's it. Thank you.